A system can be perfectly patched, fully monitored, and still silently lie to your security tools. Not because it is broken, but because something is listening between the lines of execution. That something is often API hooking, a technique that doesn't attack security head-on, but quietly intercepts the conversation between software and the operating system. Welcome to BlueHat Cybersec Academy. This piece explores how API hooking works, why it is so powerful, and why it sits in a gray zone between legitimate engineering and stealthy abuse. Let's start with the core idea, and this is where things get interesting. Modern software rarely interacts with hardware directly. Instead, it relies on system APIs, standardized functions provided by the operating system to perform tasks like file access, memory allocation, process creation, and network communication. Now here's where API hooking inserts itself into this chain. Instead of the normal flow application, operating system API, kernel, hardware, you now have application, hook layer, operating system API, kernel, hardware. That extra layer changes everything. It can observe, modify, redirect, or suppress the request entirely before the OS even processes it. And the key insight here is simple but unsettling. The application still believes it is behaving normally. It is the execution path that has been silently rewritten. Now, why does API hooking even exist? And why isn't it always evil? It's tempting to frame it purely as malicious, but that would be incomplete and honestly a bit shallow from an analytical standpoint. The same mechanism that enables stealthy manipulation also enables deep system visibility. In legitimate environments, you will find API hooking used for debugging complex software behavior, performance monitoring tools, security software observing suspicious API usage, compatibility layers translating legacy calls, and instrumentation in enterprise environments. So in other words, API hooking is often about observation and control, not inherently exploitation. The ethical divide depends on intent, transparency, and authorization, not the mechanism itself. Now let's break down how API hooking actually works, conceptually speaking, because at its core, it relies on one principle: redirecting function execution flow in memory. There are several approaches to understand this. First, there's import table redirection, also known as IIT hooking. Programs often use something called an import address table, which maps function names to memory addresses. If that mapping is altered, the program unknowingly calls a different function. Think of it like this. You change a contact in your phone so that bank silently calls a fraud service instead. The interface looks unchanged. The destination is what's been manipulated. Then there is inline function patching. Instead of changing references, this method modifies the start of a function in memory so execution jumps elsewhere. This is more intrusive and harder to detect because it directly alters executable code paths. You are not redirecting the call anymore. You are rewriting the instruction itself at the entry point. Another approach is runtime wrapping. In this case, a layer is placed around a function call, allowing inspection before and after execution. This is often used in debugging and security tooling because it is relatively transparent when implemented correctly. It behaves like a checkpoint that every request must pass through. Now let's talk about why this is so powerful, because API hooking is not about breaking systems. It is about redefining what the system thinks is happening, and that makes it especially dangerous in cybersecurity contexts. A function may report file not found, while the file is actually read successfully. A process listing may hide specific malware processes. Network data can be intercepted before encryption or after decryption. Security tools may be fed sanitized or falsified results. This is why API hooking is frequently associated with rootkits, advanced persistent threats, and anti-analysis malware techniques. At its core, it is less about force and more about perception control inside the operating system boundary. Now comes the detection problem, and this is where things get philosophically tricky. Detecting API hooking is not straightforward because the system still behaves normally from a surface perspective. Logs can be altered at the same interception layer. Security tools themselves may rely on hooked APIs. Memory level changes are subtle and often temporary. And this leads to a difficult question. If your measurement tool can be intercepted, how do you trust what it reports? Because of this, modern security systems increasingly rely on kernel-level verification, hardware-backed security features, and behavioral anomaly detection instead of function-level trust. So how do defenders respond in practice? Instead of trying to eliminate API hooking entirely, which is not practical, modern defenses focus on reducing its effectiveness. They use cross-layer validation, comparing user mode and kernel mode behavior. They apply integrity checks on critical system functions. They enforce memory protection mechanisms like DEP and ASLR. They rely on behavioral analytics instead of trusting API outputs directly. And they isolate security environments using sandboxing. The goal is not to prevent interception completely. The goal is to make manipulation detectable or unreliable enough to lose value. Now zoom out for a moment because there's a bigger picture here. API hooking is not just a technical trick. It exposes a deeper truth about computing systems. Every layer of abstraction is also a potential layer of deception. Operating systems assume APIs behave honestly. Security tools assume system calls reflect reality. Applications assume their instructions are executed as intended. API hooking quietly challenges all of these assumptions. And once you see it that way, it stops being just a malware technique and becomes something broader, a demonstration that trust inside software systems is always conditional. So let's close this out with one final insight. The uncomfortable reality is that API hooking does not hack systems in the dramatic sense most people imagine. Instead, it exploits something far more fundamental: trust in abstraction layers. And in cybersecurity, trust is always the weakest interface. Understanding API hooking is less about learning a trick and more about recognizing a pattern. Wherever software relies on unseen intermediaries, control and deception can exist in the same space. That tension is exactly why it remains one of the most important concepts in malware analysis and defensive security thinking. Now, before you go, here's your challenge and drop your answers in the comments so we can actually test this thinking in a real-world mindset. First question: if an API hook modifies a function's return value, at which layer is the truth actually being broken, user space or kernel space? Second question: can you think of a scenario where API hooking might actually improve security instead of weakening it? And third, if both antivirus and malware can use API hooking, how would you design a system that trusts neither completely but still detects abuse? And here's something to leave you with. If every system call can be intercepted, what does trusting software output even mean anymore? That question sits at the core of modern malware analysis, and it's exactly what separates surface-level understanding from real security thinking. If this breakdown helped you see the mechanics behind the illusion a bit more clearly, then like, share, and subscribe so you don't miss the next deep dive in the Malware Encyclopedia playlist, where we keep breaking down malware concepts into the logic they actually run on.